Meanwhile, so last week we learned about matrix factorization and how essentially everything that we have done is equivalent to solving the problem of matrix factorization. In fact, what we have learned last week was that everything that you have learned about supervised learning can always be written down as solving a problem of matrix factorization. Now, what is the difficult part in matrix factorization? Is that the matrix can be really long. The rows that correspond to the examples can be there can be a lot of them. Columns that correspond to feature dimensions can be really large, right? So what were some of the examples if you wanted to build the n-gram, let's say, based language model? How many features do we have? We need to now look at the exponentially many features with respect to n. And that's not that great. That's not that great. Right? And then if you imagine each row is the number of examples, it can also be very, very large. And in that case, we can't really imagine you're building the matrix explicitly as it is, and then solve the problem of matrix factorization by, for instance, solving simple function analysis, or just trying to define some loss function or the cost function that corresponds to reconstructing the entry in this large matrix based on some of the factors of this smaller matrix. So, in order to avoid the problem, we talked about some of the ways in which we parameterize these large matrices or those smaller matrices that we want to estimate in a way that is either computationally or memory-wise efficient. So, what was one of those efficient ways to do so? One of them was a continuous backover, right? Instead of looking at the B matrix or the U matrix, whichever direction you want to go to, all same thing, because we can always transpose the original matrix X or A. What we decided to do was, instead of having as many columns as there are all possible n-grams that we are counting within the context, we simply decided to have n many smaller matrices. And for each entry in this very large n-gram based matrix, we're going to model it as a sum of the entries that corresponds to the first, second, third, and all the way to the nth word in those, let's say, smaller matrices. And we just sum them up, and that's how we got the continuous backover representation. And of course, we thought that, okay, that's not really the great idea, because that's what we've been talking about, why we don't want to work in the linear space. Yep. So the idea was that we don't really want to use the linear approaches because they tend to be really nice both in practice and also in theory. Except for that, we have actually seen already at the beginning of the course or this semester that there are some inherent limitations that we pose if we use only linear computations. What was it kind of, let's say, one of those constraints or the limitations? I flew in from Paris. You all are in here, right, today. So you should remember. So what was that inherent limitation? One inherent limitation that was quite important to recall. And that's the reason why we introduce all these nonlinear layers, right? Why did we do that? Because with the linear layers, we cannot capture the higher order interaction among the variables in the input. We could only capture what kind of values those variables have, but we couldn't really tell whether a certain combinations of certain values assigned to certain variables occur. So to do so, we have to introduce a nonlinear layer. Now, do you remember the example, right? In the sentiment analysis example, the linear function, let's say, classifier wouldn't be able to tell apart not hate from not and hate, right? So, to see if there is a not hate together, and then trying to say that, okay, not hate is actually like, to make our classifier aware of this, we have to introduce a nonlinear layer. And then And then we talk a bit about how to to make it deep by having more and more nonlinear layers. And then along the line, when we talked about the transformers, we talked about how having many layers of the linear function doesn't really help. We talked about that because they can always be collected to another single, let's say, linear operation. And then so with this in our mind, instead of the continuous backover that is just summing all these vector matrix entries, we talked about how, in fact, using neural network to process the input and projecting it into a single vector corresponds to efficiently parameterizing this large, let's say, left or the right matrices in the matrix factorization. And then from there, we started to talk about, well, okay, so matrix factorization is nice, but the kind of perspective that we have when we think about it from the matrix factorization is that we're given this count matrix. We're given large count matrix. Of course, we are not often given this explicit count matrix, but we're given the data based off of which we can recover this count matrix. So we're given the matrix, and then we're trying to recover, or trying to decompose it into a smaller unit in order to get a more dense representation that's going to allow us to generalize to the unseen cases. But at the end of last week, what we talked about is that what if we look at it from the other way around? What if we say, so it doesn't really change the story, but what if we simply say that what we see in each and every entry in this large matrix is a result of some data generating process. And then often we kind of let's say acknowledge that our knowledge of the world is not perfect, nor our knowledge of the data generating process is not perfect. So we often model it as a stochastic process. So it's going to be a bit of a noisy process. And then what were some of the examples was that we talked about how we can think about generating a document. And then in that particular case, we thought, okay, how about we have some vector that corresponds to the content of this document. So we're going to draw that vector. So we're going to draw the content of the vector, content of the document. And then we're going to compare this against each and every word embedding vectors. And again, each and every word embedding vectors, what are those? Those are telling us about the content that individual word describes. And we're going to draw that vector from some distribution, and then we're going to look at the dot product in order to see what should be the distribution over the words, the vocabulary within this document. So what does it mean by within this document? Is that given the content of the documents that we want to write. And we look at some examples, right? We looked at a principal component analysis, or the very simple model that we looked at last week, like the majority of the last week's lecture. And then we did talk a bit about how about we make the content of the document to be some kind of the same mixture of different topics. So we did talk about how to get the one hot, not the one hot, but the point in the simplex as a content of the document, plus having all those topic vectors. Right? Mm-hmm. And then what are those topic vectors? Again, those vectors are going to be drawn from some, let's say, distribution where the content of the topic is described. And what was the third approach that we talked about? Yeah, at the very end of last week's lecture.
Other reversal model?
Sorry?
Other reversal model?
No, we did talk about other reversal model, but that's not the final one. But there was one more. Mixture of framework, right? We talked about that. And then we talked about how the autoregressive model is yet another one, where autoregressive model does not have any, let's say, global content or a vector that corresponds to global content of a document. So in the case of the autoregressive model, we're just trying to predict what the next word should be given what we have generated. There wasn't anything that actually tells us or indicates that the global content of the document. All right, good. Okay, so that was a kind of, let's say, beginning of the generative story. So in fact, today's lecture is going to be the kind of final lecture of this semester on any of these technical materials. And from next week, next week I'm going to give, I'll talk about a bit of limitations of these statistical approaches, in particular in the context of the natural language processing. And week after, there's a Thanksgiving week, so they take a week off. And then after that, so in December, we're going to have 2 guest lectures in 2 weeks. One of them is going to be given by my PhD student, Aishwarya Kamat, who's going to tell us about the multimodal learning. So at the end of the day, what is the one thing that we almost we know for sure with a very high certainty that any intelligent organisms have is that they have access not only to a single sensory organism but the multiple sensory perceptions. Right? In our case, we see, we hear, we touch, so we feel, and then we can taste, we can smell, and on, right? So then, it's probably a good idea to think about what is the right way to do that kind of multimodal processing in machines as well. So Aishwarya is going to talk about that one. And the week after that one, which will be the final week of this course, that we're going to have the Kunu Choi, he's a research scientist or the senior research scientist. I forgot his latest title at ByteDance. So he used to work at Spotify. He moved to ByteDance about a year and a half ago. And he's going to tell us about what if we do exactly this, all the things that we have just learned in this course, but not with language, but with music. It turns out that you can do exactly the same thing with the music, and it actually works pretty well. So that's going to be the kind of final wrap of what if we go beyond natural language processing? And as an example, we look at the music information retrieval. And if you're interested in it, you should check out the conference that is ongoing at the moment this week called International Symposium on Using Information Retrieval. Actually, you'll be able to read all the papers there because as long as you're interested in using audio processing, because all the techniques are exactly the same thing that you just have learned. Well, that's it. Okay. So let's continue on. Let's delve into what we're going to talk about today. But before that, any questions so far on what we have just reviewed, and then you preview as well? All good, all good. We're going to go into a bit more probabilistic route today. So we'll just come back to principal component analysis. So we learned about what principal component analysis is last week a bit, but the assumption here is that if you actually have taken any of those the prerequisite courses, principal component analysis is one thing that you probably have learned already. So we're going to look into the probabilistic version of the principal component analysis. And let's zoom out, and then we're not going to talk about natural language for the first, half of this lecture. So what we need to do to make a probabilistic version of it, you need to think about what is it? Data generating process. You always need to think about data generating process. And in data generating process, there's always a one variable that's going to be, or can be multiple, but at least one variable that is the one that we observe in the data. So we're going to say it's going to be X. And whenever I use a circle, that means that there's a random variable. So there is some noise involved in this one. And then this data that I'm going to observe, this X that I'm going to observe, I'm going to assume that this comes out of 3 variables. One is that there is some hidden variable C that tells me about the content of X. So you see the difference here, right? So the content does not necessarily mean what we see, what we read, because the same content might be expressed in many different ways, right? When we write it down, and then we can also figure out what the content is based on the text, but they are not same. So there is a content, there is an abstract concept, and there's the actual observation. And we are going to say that this Z gives a rise to X. So this is going to be our data generating process. Extremely simple, right? And then whenever you have this kind of data generating process or the probabilistic graphical model, what you need to define are some of the distributions. Now, first thing we want to define is what is the distribution of CC? So what this data generating process tells me is that I'm going to throw a sample of C And then given that samples of Z, I'm going to compute the conditional distribution over my observation X, from which I draw a sample of X. That's my data generating process. And to do so, first step is to define a prior distribution over Z. So there is a variable that we don't know. Now in this case, we call it prior distribution because this is a distribution that we have to define without looking at any data, right? So before knowing anything about the actual data that has been generated, what is the distribution from which this Z should be drawn or sampled? We're going to assume that the Z is from zero mean Gaussian with zero mean unique covariance Gaussian. It's going to be D prime dimension. So it's always a kind of a reasonable thing to say that if you don't know anything about it, you say that we'll just use a standard normal distribution. So that's what we're going to do. We're going to say it's a standard normal distribution. Center is at the origin of this D prime dimensional space. And then the covariance matrix is going to be diagonal, and the diagonal is going to be just all ones. What that means is that it is every dimension here is decorrelated, right? So changing another one dimension shouldn't really change another dimension. It is up to, let's say, second order moment. But in the case of the Gaussian, that's actually independent. So all of them are independent. And then for each of the dimension, you can imagine that having a very simple standard Gaussian. And then the second thing that we need to do define is a conditional distribution over X given Z. Now I have drawn a sample from Z from this standard normal distribution. Now what should be the conditional distribution over X? Now this is the part that we cannot simply just make up, right? Because what kind of observation are we talking about? So that's going to tell us a lot about the conditional distribution. And then in fact, what we've been doing all along tells us about how we can define such a distribution over some fixed vocabulary, or even entire, let's say, sequence space. But here for now, to make the conversation a bit lightweight, we're going to assume that this also follows a normal distribution. That is, this X given Z is going to follow a normal distribution where the mean is going to be W times Z plus B. And then our covariance is going to be, let me see, sigma squared identity, D-dimensional identity. So we'll just assume that it's just Gaussian. So what does that mean? And then this Gaussian is going to be D-dimensional. So what this says is that if we draw a sample of Z from a standard normal distribution, and then given that Z, there is a content of our X, the observation. Our observation is going to be a noisy version of some affine transformation of Z vector. And then we add some noise. Because we know that our data generating process is not perfect. There has to be some uncertainty within this data generating process. Yes.
Where do W and B and sigma come from?
Oh, I'm going to say we know what those are on the data generating process part. We just said that we get this W, which is going to be D by D prime dimensional matrix, and then B is bias vector. It's going to be D dimensional vector, and then sigma square is going to be, let's say, just scalar, a positive scalar, or the sigma can be anything one. So this is how we define the data generating process. And then this is another way to write the same thing, a bit more traditionally, is that we say that X is the W times Z plus B plus epsilon, where epsilon is a sample drawn from zero signals. The zero mean normal distribution with the diagonal covariance, where the diagonal entries all are just sigma squared. So it's like somebody gave me Z, that is the content of X, this observation. And what we are saying is that the content is transformed using W and B. But then because this data generating process is not perfect, there is always a bit of a noise that is added. So that's the part that we cannot resolve based on our knowledge of the data generating process itself. Okay. Now, for W and B and sigma, what we're going to say for now is that the sigma is fixed. We're going to say somebody gave us this sigma square. And then W and B, we're going to estimate them. So what do we mean by estimate is that in order to estimate W and B, we cannot really estimate it without having anything, right? We're going to estimate it based on what we observe. Based on what we observe. So for now, we can just say that, okay, those are given as well without too much work. Anyway, so let's see what is, so here's the one that is unobserved. So Z is unobserved. X is going to be what we are going to observe. And then W and B are parameters, and then sigma squared tends to be hyperparameter. We can't really fit sigma squared by using data. Why is that so? Because if you only use the actual observed data, then what is the best way to fit it? We say that there is no noise. Whatever we have observed doesn't have any noise. So sigma squared, this noise can only be estimated using a held out set of examples. So this is a very tricky part, but it's not really important in our case, so we're going to just continue for now. Now, once we have these two distributions, one is the prior distribution over Z, and then the other is the conditional distribution over X given Z, we can define three additional distributions out of it. The first one is the joint distribution. The joint distribution, under joint distribution, we define the probability or probability, mass or density, it doesn't really matter. They are at the end of all the same thing. P of X and Z. So this is the joint probability distribution over both the observed and hidden variable, X and Z. And then this can be rewritten as a P of X given Z. So the conditional times P of Z, the prior. And we already know what the prior and conditional are, so we can actually define, we can compute this joint distribution. So what is the next one that we can compute? We can now compute the marginal distribution as well. Then here, the marginal that we are interested in is P of X. So what if I observe one X, particular X, under my data generating process, what is the probability of the observed variable X? And then that's the marginal distribution. In doing so, we start from the joint distribution. And then we're going to marginalize out Z. And then what you see here is that this is identical to computing the expected log X given Z under the prior distribution. Okay, so that's a marginal distribution. The third one is what we call posterior distribution. And here, the goal is that we now have observed X. We have observed X. Now I want to know what is the content that has given a rise to this observation. So what was the value of this Z that gave rise to what I have just seen? Right? So that's the posterior distribution. So why is it a distribution? Right? It's that as we said earlier, there are many different ways in which the same content can be written, but then also the same article may actually describe a slightly different possible content. Right? Sounds a bit weird, but that's true, right? Depending on who reads it, who wrote it, sometimes it's a bit ambiguous. What is the precise content or the topic that is being discussed in that article? And then, so what happens is that given an article or some kind of observation we have, we can now imagine what are the possible values of Z that have likely given rise to this particular observation or the article here. So that's the posterior distribution, and then this can also be computed because now this is where we use the Bayes rule. is that this turned out to be same as a ratio between the joint distribution and the marginal probability. If we write it once more, it turned out that this is really same as is this. What it means is that if we compute this joint probability and then normalize it so that it's going to sum over C, right? Then we can actually compute this posterior distribution. So these are really important concepts that you should just know, not only because of the natural language processing, but just generally in modern day machine learning. So we start with the data generating process. That is what we think gave rise to the data set of the observed variables that we see. And then once we have this data generating process, we now can define the actual probability distributions. Often in machine learning, we don't tend to go too crazy about the idea of defining this data generating process too complicated. Instead, we're trying to just make sure that this unobserved variable, such as Z, is there to give rise to these observed variables, because there could be multiple observed variables. But then we need to have the hidden variable that's going to model all these dependencies among all those observed variables. We're going to get to that shortly later today. But once we define it, we now need to define the prior distribution over this C, the content that gave rise to the observation, and then the conditional distribution that tells us how the content is turned into the actual observation. Given those prior and conditional distribution, we can now talk about the joint distribution of the observation and unobserved variables. Obviously, starting from here, we marginalize out the Z, the unobserved variables, then we end up with the actual marginal probability assigned to any observation, again, under this data generating process. That's very important. All these distributions seem to be pretty much defined on its own, but implicit is that every distribution I have written down here is conditioned on the particular data generating process that we have drawn. And then the interesting thing you notice in this particular form of marginal distribution is that what is the probability of any particular observation? We're going to go through all possible values of C. And then we're going to see which ones are more likely and less likely because we know the prior distribution. And then we trying to essentially compute the weighted average of the probability assigned to this observation X given a particular C. So you can imagine that what is the probability of this observation? Let's say this observed article. You can imagine that I'm going to consider all possible contents, right? That's C. And then given that C, I'm going to write the article and then see how similar this article is to the actual observed article. If it's similar, we say that the high probability given this content. And then we're going to try all of them and then do the average, let's say, probability assigned to the observation. So that's the marginal probability. So this is interesting if you are interested in looking at how likely this article is under this data generating process. But often what we want to know is that what was the actual topic or content that was behind this observation. And that's the posterior distribution. And then this posterior distribution, what it tells me is that let's try all possible Z values. And then we're going to say that Z value should get a high probability if the Z value gave a rise to this particular article with a high probability and is also likely under prior. So it's a mix of how likely is it that an author chose that topic. If the topic itself is extremely unlikely, whatever the article I see, it's very unlikely that the topic of this article is about that rare topic. So that's the prior part. The first part is that now if I imagine that the topic was indeed the case, how likely is this article given that topic? So we look at that mix, and then that's going to be a posterior distribution. Back to principal component analysis, because except for the fact that we are using normal distributions, there has been nothing about principal component analysis when we define these three distributions. Some nice properties of normal or Gaussian distributions includes one, marginals and conditionals of Gaussians are Gaussians. So what that means is that the so here this is a marginal of Gaussian because the joint of the two Gaussian variables is also a Gaussian variable, a Gaussian distribution. And then marginal of a Gaussian distribution is also a Gaussian distribution. And then that's really, really nice. That's really, really nice. In our case, because we now know suddenly, by the virtue of having Gaussian prior and Gaussian conditional, we know now that everything here is Gaussian under the assumption that the mean is computed in the particular way. And what's the second property that is really nice about this normal distribution is that if any normal distribution you choose that's fully characterized by just two parameters, mean and covariance, nothing else. As soon as you have those two parameters, you know precisely which Gaussian distribution you are talking about. So then let's do some simple algebra here. All right, so let's keep this in our mind as we go forward. So there was a prior distribution and there was a conditional distribution. Now let's look at the marginal distribution. So we said that we could write x as the w times z plus b plus epsilon. This is identical to saying that our conditional looks like this. So our conditional is Gaussian with the mean w times z plus b, and having a covariance sigma square is identical to is equivalent to saying that the x equals w times z plus b plus epsilon, where epsilon is a centered, so zero mean Gaussian distribution with the same covariance matrix. So we're going to just stick to this one and then see what happens. So one thing, what do we know? Marginal distribution is also Gaussian. And then Gaussian is fully characterized by two parameters, mean and covariance. So all we need to do is compute the mean first. So what is the mean of this x here? And then if you recall from the probability 101 course or something similar, expectation is a linear operator. We can just push through all those linear computation, then we end up with w times expected z plus b plus expected epsilon. Now, what was the expectation of epsilon above? If you recall here, 0. This is just 0. And then what is the expectation of the z? 0. So this whole thing is 0. So what that means is that the marginal, so the mean of the marginal distribution over x is just b, the bias factor. Now this actually tells us a lot about and this actually answers the repeated question that I got about what does the bias do. If you recall from the very first week of this course, you all had a question about what does that bias do? And then my answer has been that well, that's the value that the target is going to have without have we not seen actual input. Right? Without looking at the input, what should the value be? And then that's precisely the case here, right? So what is the expected value of this article? Had I not seen what my content is, that's the bias, right? So that's the bias. Now let's compute the covariance. So what's the covariance of x? Now covariance of x is the outer product of the centered x. And this can be written down as the expectation of the wz plus epsilon, wz plus epsilon transpose. So where did the b go, right? So the bias is disappeared because we now know that the expected x is biased. So we're subtracting the bias and then from the WZ plus B plus epsilon. So what we end up with the WZ plus epsilon only. And after doing a bit of a couple of lines of the expansion further, what we end up with is W transpose plus sigma square I. So how did we get here? Let's look at the first terms from the both sides. So we get a W times Z transpose times W. And then we have the Z times Z transpose, and then the expectation is a linear operator. We push it inside. What we get is that the W times expected Z times Z transpose times W transpose. What is the expectation of the Z times Z transpose? That is a covariance of Z, which is just an identity function. So that one just disappears. So we end up with the W times W transpose. And then now let's look at these cross terms. So we have the W times Z times epsilon transpose, and also epsilon times W times Z, epsilon times Z transpose times W transpose. Again, expectations, we push it all the way. Epsilon has a 0, Z has 0. So they just disappear. And then we end up with the epsilon times epsilon transpose, and again the expected, let's say epsilon times epsilon transpose, the covariance of epsilon, because the mean of the epsilon is just 0. And what was the covariance of epsilon? That is the sigma squared times the identity function. So this is what we get, and then these two things, so the B and then W times W transpose plus sigma 2 square, sigma square identity fully characterizes this marginal distribution that is normal. Okay, so far so good? Yes. Very clear, right? It's just expectation here and there, and at the end, most of them are 0, it turned out. Now, let's just look at a limiting case of what if sigma square was 0? So we say that our data generating process is perfect. There's absolutely no noise going from the selected topic Z to our observation X. Then expectation stays same. Expectation stays same, but the covariance changes a bit. Then covariance becomes W times W transpose. And then how do we actually find this W and W from the actual observation? So this is the covariance matrix of the marginal coming out of our data generating process. But then once we observe many X's, right? If you have a data set of many observations, we can estimate the covariance of the X from the data. And then what is the right way? What do we want to do? We then want to ensure that this W times W transpose is going to be similar to the empirical covariance matrix that we have estimated using the data points. And the same thing with the B. Now, in the case of B, it's very easy. So we're going to look at all those observations, compute the average, and then that's going to be our best guess or maximum likelihood guess of what this bias should be. In the case of W, you see this format here, right? What this form tells us is that we need to solve the problem of Eigen decomposition of the covariance matrix. Covariance matrix is by definition symmetric. And then we can actually solve the eigenvalue problem. So I do the Eigen decomposition in order to compute the W and W directly from the covariance matrix. What does that mean? It actually means that this is equivalent to the matrix factorization view of the principal component analysis. And furthermore, it is equivalent to the view that PCA is finding the directions that have the maximal variance. And then how you do that is to actually compute the covariance and then trying to do the Eigen decomposition and then take the few top principal components. Then it turned out we end up with the exactly same formula in the limit of 0 noise in the observation. So just repeating myself once more, just like what I did last week, is that it's just another way to look at the whole thing. Right? Matrix factorization was there last week. This week we're looking at this generative modeling part. But they end up often being very same, except for noise. So what data generating process gives us is for us to express what we believe went behind the data that we have collected. And then the second thing is to express our way of uncertainty, right? So we cannot know the perfect process by which the data was generated. If we knew like exactly, and then if we have to solve this really well, we're going to just put a huge amount of compute to try to just invert the process. But the important thing is that even if we want to do so, we often know that our data generating process is imperfect. What is the data generating process of a book? We know that a person wrote it, okay? A person, a group of people, but what was the precise mechanism by which that was written down, starting from the actual topic that we don't know what that is? We actually don't know. So we have to encode our lack of knowledge or the incompleteness of our knowledge, and then that often shows up as this kind of noise-related variables or the parameters. Okay. All right. So then let's think about learning in this. So in other words, this is uninteresting. So we're going to consider the case where we actually know, we say that the noise exists. Then how we do the learning? We're going to do the usual log likelihood learning or the maximum log likelihood learning. So what do we want to do? We're going to write down. So we have a data set of many examples, x1 to xn. And then what is the log probability of this data? What is the log probability of this data? But I'm going to actually make a small change here saying that, okay, this is given WB and sigma squared. Then I'm going to skip it whenever it's not really necessary. So this is implicit. So what it means is that just like what I said earlier, all these probability distributions seem to be the distribution over these variables, but they are all implicitly conditioned on our choice of this data generating process. And then large part of our choice of the data generating process consists of the dependency structure, the arrows, and then the choice of the distribution and the parameters. So we can be a bit more explicit and say that this distribution over the data is going to be conditioned on the parameters, but we'll just assume that they are written down. It's just too cumbersome to write it over and over. Then what we end up with is, because we assume that our data points were sampled from the identical distribution, and then they were sampled independently from each other. So then what that means is that if you write the P of x1, x2, all the way to xn, because they are all independently sampled, we can just write it as the product of P of xn, right? So the n going from 1 to capital N. So that's what we're doing, but of course we're working in a log space. We end up with this. xn WB sigma squared. So this is the marginal distribution. And then we now know what the marginal distribution looked like exactly, right? So expectation is B, covariance is W times W transpose plus sigma squared. What that means is we can write it down very, very carefully as xn minus B transpose W transpose plus sigma square I inverse of that times xn minus B minus, I need to be careful about one, yes, minus 1 over 2 log of the determinant of the W transpose, W times W transpose plus sigma square I minus D prime log 2 pi. Looks familiar, right? This is just a log probability density of a normal distribution. So there is the first part is telling us that if the observation, that is the xn, is close to B, then the probability will be high. But then, of course, not every dimension is equally important. The importance is given by this inverse covariance matrix. So this whole term is often referred to as Mahalanobis distance as well. And then the second part, this part is now these two terms corresponds to the local partition function. So we need to ensure that the probability density integrates one. So this is what it does. An interesting thing here is that the log partition function is not a function of the bias or the mean, because regardless of where you are, the volume doesn't really change of the Gaussian distribution. So it doesn't depend on the mean, but it depends on the covariance, because covariance tells us which directions are really important. So what we do is that based on the importance, we compute the volume that is taken up by this Gaussian distribution. And then this is the part that we say that, oh, this volume has to sum to 1. Now this is just a kind of the same, making sure that this 1, not like the square 2 pi or square root of 2 pi. And then now let's see. How are we going to solve this? There are many different ways to solve this problem with respect to B and W. Now, in the case of the B, you can kind of see that, okay, so it probably is going to be mean. So my suggestion is for your exercise, try to maximize this entire thing with respect to B and W yourself by hand, and then see if you end up with the exactly same solution. But I'm going to just tell you the answer here, is that the optimal B that's going to maximize this whole thing is going to be truly the average of all those observations that we had, and then optimal W is going to be, yes, optimal W is going to be the how did you actually? So you actually end up with the Eigen decomposition of the regularized, let's say, covariance. I'm actually blanking out on the sign. Should it be the empirical covariance plus sigma square or the minus sigma square? I guess it's that it has to be plus. You never subtract anything. I'm blanking out. Okay, so well, it's your exercise, so you'll do it. All right. You do it at home, but I'll give you a hint. That is that to compute this, you need to compute the derivative of this loop determinant, which is a bit tricky. But I'll just give you the actual value. You need to compute the gradient here. It's going to be 2 times the trace of W transpose plus sigma square I inverse of W. Now, with this quantity and then the gradient you get from the first term with respect to W, you can write down the analytical form for W. Somehow I'm blanking out. Too much flying. But yes, it is your own exercise. Try it out, and then you're going to see that this is why PCA, or assuming that every distribution is Gaussian, is beautiful, because you can actually write down almost everything, and then you get the analytical form of them. Yes. Okay, so this is a marginal distribution. So why did we actually compute the marginal distribution? Because marginal distribution allows us to compute the probability assigned to the entire data set. And then now based on this, we can infer or estimate all those parameters of this data generating process, so that with those estimated parameters, our data generating process is better aligned or well aligned with the actual data that we process. All right, let's continue with the next distribution. So that was marginal. Let's look at the joint distribution. X is Gaussian, Z is Gaussian, and then their relationship is linear. And what they mean, and then also their mean, and then what it means is that we do not actually make the covariance of the X given Z conditioned on Z, which means that if we just stack them up, we're going to end up with another Gaussian distribution. This is a really nice result. But again, a lot of things are for you to, for your exercise, your own exercise. So I'll just write it down for you. So in this particular case, joint distribution over x and z. So we're going to look at the stack of these x and z variables. Again, under this assumption, right? Under this assumption. So the mean of z is zero vector, covariance of z is just a constant, right? So they don't depend on x. And then the mean of x is going to be this linear function of c. And then the covariance of this conditional distribution is going to be a constant. So under those, let's say, assumptions, what we had was that we ended up with this marginal distribution over x. So marginal distribution of z is the prior that we have defined. And with that conditional distribution we have defined, that is just a linear function of c, we end up with the marginal distribution over x, where the mean is b, the bias, and then the covariance is w times w transpose with some regularization, that is adding some values in the diagonal. What that means is that if these two distributions, so distribution over z and distribution over x, have nothing to do with each other. The marginal distribution over x is not conditional on z at all, right? It's just b and then w. That's it. So what that means is that we can just stack them, and then that's going to be another Gaussian distribution. It's going to be just a d plus d prime dimensional Gaussian distribution. And then what would be the mean of this x, z concatenated vector? It's going to be b and zeros, right? It's just concatenating the mean. Then covariance of, okay, so we have to be a bit careful here. So the covariance of x, z can be written down as covariance of the x alone, covariance of the z alone, and then cross covariance from x to z, and then cross covariance going from z to x. And because covariance matrix is always symmetric, we need to now just look at these three entries. What are these values? Now we know the covariance of z alone very well, identity. And then what is the covariance of x? W transpose plus sigma square, identity. Now then the question is, what is this xc, sigma of xc? We can write this down pretty easily by saying that the expectation of x minus expectation of x times z minus expected z transpose. So this is we're looking at the cross covariance, and then what we end up with, just doing exactly what we did earlier, we end up with the wz plus minus plus epsilon times z transpose. Why is that? Because the expectation of x is bias, so bias cancels out on the left side, and then expectation of z is 0, so we just end up with c. And by writing down further, we get the w times expectation of z transpose minus plus expectation of epsilon z transpose, and then epsilon and z are independent from each other, so expectation can be pushed into either direction. And these are all 0. And then this one is identity, so we end up with w. And because this covariance matrix is symmetric, what is the sigma of the zx is going to be just a w transpose as well. So we can now get the joint distribution perfectly, again, as a Gaussian, defined using, fully characterized using two parameters, mean and covariance. Now, let's see. Okay, so far so good. Why? But are we actually interested in this joint distribution? Joint distribution, we are never interested in joint distribution. But joint distribution is interesting because in order to compute the posterior distribution, we need the joint distribution on the numerator. So the denominator is uninteresting. It's just a normalization. We just ensure that this distribution over Z sum to 1, but the numerator is the one that is interesting, and that's just joint distribution over X and Z. So that's the reason why we compute this. And what was a nice property of Gaussian again is that the any conditional induced by the Gaussian joint distribution is again Gaussian distribution. So then let's try to compute the posterior distribution. So the posterior distribution. So this one definitely a very fun exercise for you to do, but I tried it while I was preparing this, but I'm not going to do that myself. I've done it enough, and then I don't want to do it anymore. But the most important thing is the Gaussian distribution. It's really important. So we need to look at the expectation or the mean, and the mean is going to be 0 plus sigma zx sigma xx inverse times x minus b. Is equal to W transpose W transpose plus sigma squared identity inverse x minus b. Now the covariance is going to be sigma zz minus sigma zx sigma xx minus 1 sigma zx. And that's going to be identity minus W transpose plus sigma square I inverse W. What's okay? Oh, okay. So let's get the first one. So now the goal here is that okay, I've seen now X. I want to see what was the actual content of the Z, content of this X, right? And then there is Z. And what we end up with here is that we look at X, we subtract the bias. So subtract the component in this observation that doesn't really depend on the content, right? So we're going to remove that part and then look at the actual content related portion of this observation. And then what we do is we are in fact solving. So let's say Z sigma square is just 0. What is this W transpose times the inverse of the W times W transpose? It's pseudo inverse, right? So given this W, because the X is the result of applying the affine transformation to Z. So how do we actually solve for Z given X? Is that we're going to subtract this bias. So non-Z related portion, remove it, and then we multiply this X with the pseudo inverse. To find the Z that's going to get me the most likely Z in this linear map. Makes sense, makes sense, makes sense. And then this just fell out of this, let's say, probability formulation. Now, this makes sense, and then it's easy to look at, but this is easy to look at because it's linear formulation. But what we know now is that if we chose this kind of linear formulation of the data generating process, we recover the original PCA formulation. And then, but that's not the point. The point is that, okay, so then what would happen if we make a more complicated data generating process? Can this whole procedure of probabilistic approach get us a more complicated data generating process and then allow us to use the kind of complicated data generating process? But we'll get to that one. Okay, so this is it. But this is a bit weird. This covariance part is a bit weird. So what covariance tells us is that so this whole thing tells us that, okay, posterior distribution is Gaussian. So what it means is that there's in fact a one very likely content Z that gave rise to this observation X. But then, of course, we have some uncertainty surrounding. There aren't, let's say, many different Z values that could give rise to X, but there's just one. But then this covariance tells me how certain I am about this choice of this recovered Z. And it turned out this covariance is not a function of X. It is in fact just the identity matrix minus the pseudo inverse the regularized pseudo inverse multiplied to this W. And then it's not a function of x. What that means is that in this particular formulation of principal component analysis for the probabilistic version, the covariance matrix over our guess of what the Z should have been, that uncertainty doesn't depend on x and is same for any x we see. This actually makes it a bit less interesting as a kind of, let's say, probabilistic mode. Makes the PCA as less interesting as a probabilistic, let's say, model, because we often, what we really want to know is that we got the estimate posterior, let's say, mean of the Z given x, and then we want to know how good our guess is for each of the input separately. Because for some observation, we might know that this has to be about this particular topic. Absolutely no uncertainty. For some other observations, maybe it was written too vaguely, and then you can't really tell precisely what the topic is. So we want to have a large variance. But the PCA doesn't actually give us that ability. For PCA, regardless of what the input is, our uncertainty is fixed. All right, so far so good. Yes. Now we want to slowly move toward handling natural language text with this kind of principal component analysis or the probabilistic approach. Clearly, linear model, not realistic for us. And also, having a Gaussian distribution over the text doesn't make any sense, right? What does that mean? So we're going to relax that one at a time in the rest of the lecture. All right, we're running out of time. Let's take 4 minutes break. And we'll come back at 6:08. Reason. All right. So we go from x equals the linear transformation of Z plus a noise, and to x being the noise added to some arbitrary, potentially nonlinear transformation of Z. And then doing so is better because it's not linear anymore. So you can actually model much more complicated mapping going from this content Z to the observation X. However, we lose one nice property of marginal being Gaussian. So with this new formulation, a more relaxed version, we can't really guarantee that the marginal distribution is going to be Gaussian. And in fact, more generally, the marginal distribution is going to be an infinite mixture of the Gaussian distributions. So for every Z, we have a new Gaussian defined there. But that sounds a bit wrong, right? So how can that happen? So it turned out that this is not really like the almighty model just because we use the same function f at every location. So we don't have, let's say, the infinite number of the completely free, like whatever they can be Gaussians, but rather we have a mixture of the infinite Gaussians that are constrained by the choice of this f that is shared across all those Gaussian components. So we are going into essentially nonlinear principal component analysis. Principal component analysis. Now, in this case, what we are almost always more interested in is that when I looked at x, what was this Z that gave rise to this x? Right? So we want to look at the posterior inference. So let's think about the posterior inference. So trying to infer what the posterior distribution over Z is. And we're going to just even look at what, okay. So this is trying to compute P of Z given x when this f is not anymore linear map from Z to x. It turned out that this posterior inference problem is generally intractable. That is that we don't know how to characterize this distribution in a polynomial time. In fact, if we put some, let's say, conditions such as, let's say, Z is not really the real value, but it is a discrete value, or we're using some kind of low precision, right? Because we don't have the infinite precision. then we can actually solve this problem, of course, almost perfectly, as long as z is bounded, but that one is it's either NP complete or the sharp P complete. I think the sharp P, yeah, because the posterior inference cannot has to be more difficult than NP complete, because if you can do this, then we can solve all the other NP complete problems as well. Very easily, very easily. Too easy, too easy. But anyway, generally, so we can't really solve this problem. In practice, for a number of reasons beyond just computational complexity. One is that we don't even know the shape of this distribution. So before, what was the amazing thing? It was Gaussian, Gaussian, and then we wrote the marginal, which was Gaussian, and then the marginal over X was independent from the prior distribution over Z. So the marginal was Gaussian, and then the condition of the Gaussian, that is posterior distribution, so Z given X, was also Gaussian. Nice. So we need to figure out mean and variance. We don't know what this distribution looks like. This distribution can be arbitrarily complicated. And then if you don't know the shape of the distribution, then we need to somehow come up with a way to characterize it using some kind of non-parametric approach. That one is not trivial either. And then how to do the inference using the kind of non-parametric turned out to be quite difficult. So what people started to do is to say that we're going to just give up on doing the exact inference, but we'll do the approximate inference. And there are many different ways to do approximate posterior inference, such as using Markov chain Monte Carlo methods or expectation propagation. Probably not a lot, and many other approaches like the Laplace approximations and whatnot. But here we're going to look at this technique of the variational inference. In variational inference, our goal is to find a tractable proxy distribution. Then this tractable proxy is going to be Q of C. Or sometimes the people write it as Q of C given X. But the more appropriate way to say this is that we get Q of C for each and every individual X, because the choice of the Q does not have to be shared across all different X's. You can have a different Q for different X. But let's say Q of C or the Q of C given X. And then what is the goal of this approximate posterior inference is to find this tractable proxy Q of C that's going to be really, really similar to P of C given X. When we think about the similarity between different distributions, it's actually not that easy to choose one particular way to define this difference. Do we want that difference to be symmetric? Maybe, maybe not. What should be the measure of this similarity? It turned out that in the case of the approximate posterior inference, we actually have a pretty clear criteria that we want to hit or satisfy with the choosing a metric that we use, not the metric, but choosing a quantity that we use to characterize the similarity between P of C given X, the true posterior distribution, and this proxy or the variational posterior distribution. What are those criteria? One is that our goal often is not to exhaustively figure out all possible likely Z that have given rise to this observation. We often want to know one or two few possible Z values that have given rise to this observation. So in that, what that means is that we want this Q to find or to fit one of the likely, let's say, configurations under this distribution. That's one thing. And then the second thing is that if we want this quantity that tells us about how similar these two are to be easily computable. Easily computable as in there has to be a computationally efficient way to compute that directly or approximate them using some kind of sampling algorithm. It turned out the KL divergence is a pretty much perfect choice. And the KL divergence is not symmetric, unfortunately. So it's not really a distance, but it's a divergence that measures the similarity between two distributions with an order in between. And in this particular case, it turned out that using a KO divergence, no one agrees on what is the right way to read this. Everyone agrees on KO. Everyone agrees on this. So this part, no one really agrees on it. Some people say we should read it as a KL from P to Q. Some people say it should be KL from Q to P. Some people say KL, Q, and P. And some people say that we should just call it all. Just write it down, and then I hope that everyone can read it together. But so we're going to just go for KL, Q to P for now. I think that's easier to remember. Then it's defined as the negative expectation of log P of C given X under the proxy distribution plus the entropy of this proxy distribution. Well, let's try to look at it separately. So the first one, let's think about this expectation. What this expectation says is that we're going to go through all possible values of C, but we are only interested in Z's that are highly likely under our proxy distribution. We don't care about the entire space of C. We only care about the subset of C that are highly likely under this Q. And then we try to look at how likely those Z values are under the true distribution. So this is the kind of first criterion we talked about. This is we don't care about the all possible, let's say, highly likely values of C's under the true distribution, but we want to find one or two very likely Z values under this Q distribution. And then this is what it tells us. If I choose a simple enough tractable proxy distribution, then the area or the subset of C's that are highly likely under this Q distribution is going to be in the small neighborhood. So imagine that this Q is going to be a Gaussian distribution. Then all these likely Z's are set, around this mean of this Gaussian. So we only check that. And then we try to see if that portion, the subset, receive high enough probability under this true posterior distribution. And then we look at we negate it just because this is a divergence. The smaller, the better. Smaller, they are closer to each other. And then what is this one? This is the entropy of this Q distribution. If you recall entropy, because we talked about the entropy quite a bit when we talked about perplexity. And then one easy way to think about what entropy does is that in particular, so this is not really like the entropy. Entropy is a differential entropy because the Q can be a continuous distribution. The entropy is essentially the size of this subset of the Z's that receive a high probability density under this Q. So we're going to look at some, let's say we're going to set some arbitrary threshold. We say that if any Z that receives the probability density that's greater than some epsilon is a highly likely Z under this Q. And then now I can find all these subsets or the subspaces of C that only contains this highly likely Z. And then this entropy is the volume of them. And then what it says is that the lower, yes. So that's the volume, and then we want this if the volume is high. Wait, hold on. Okay. So we want this volume to be high. But this entropy is the minus of the volume. So this is the negative volume of that one. So it's a bit confusing. I think it's, we all blame closed channel for putting minus sign there for when you define the entropy. So everything is so confusing, but this is a minus of the volume. And then what it says is that they are close to each other if the volume is big. The volume of the Q is big. So these are two things. So one is that we are trying to identify a small number of likely Z values under the true distribution. And then the second thing is that we, however, trying to ensure that we're not going to just find one value. Right? We're not going to just find one value because what is the easiest way to do so is that make this Q to be delta distribution. So it's going to be zero everywhere except for a single Z value that receives a high probability under the true posterior distribution. to make this value really, really small with the negation. But then the second term is essentially counter that, saying that, well, you can't really do that. Your volume has to be as large as possible. So if you go look for this scale divergence in Google and whatnot, you're going to look something like this. Some let's say illustration showing that well, here's a very complicated true distribution P. And then if we try to minimize this scale divergence with respect to Q, because P is fixed, right? True posterior is true value fixed. Then this Q distribution, if it's a Gaussian distribution, is going to look something like this. So it's going to have some small, let's say, subset over which the Z gets a high probability density according to this Q. And then under this small subset, we want to ensure that this the Z's receive a high probability under this true posterior distribution. And then now, why does it actually try to fit it like this? Because of the second term, because the volume has to be. But if it's too big, then this part is going to penalize, because the true under the true posterior distribution, the Z doesn't receive the high enough probability. But this is too simplistic, right? Whenever you see some illustration on the internet saying that, so here's a one-dimensional example, two-dimensional example, three-dimensional example, and then this actually explains everything. You always be very skeptical, because one thing for sure is that the high-dimensional space looks very, very different from the low-dimensional space. But that's it. All right. So then what do we want to do in this variational inference, or the approximate, so the variational inference is to minimize this scale divergence from Q to P with respect to this Q. So we're trying to find the Q that's going to tell us that. It turned out to be quite, it has a very interesting property. So let's start from the KL Q2P. This can be written down as a negative expected log probability of X given Z under Q plus the KL divergence from Q Q to P again plus log P of X. This is just a weird way to rewrite the whole thing. But one thing for sure is that this KL divergence is always greater than equal to 0. If KL divergence is 0, Q and P are exactly the same. But otherwise, there is always going to be positive. And then what that means is that we can rewrite the whole thing a bit by saying that the P of, so the log marginal probability of X, so we observe one X, and then what is the marginal probability, is bounded from below by the log probability of X given Z under this Q distribution minus the KL divergence going from the, oops, I'm sorry, I think I forgot to actually be more specific here. Z X P of Z. So here this P was P of Z given X, right? So it's a bit confusing. Totally understand. And then Q, Z, and PZ. If you recall from last week, I said that the P is one of the most overloaded, let's say, the symbol in the probability and the mathematics in general, and that happens here. So you can actually derive this from the KL divergence. You can do the exercise, but what you end up getting is that the log probability of X is always greater than equal to these two terms. This the right hand side. That is at the expected log probability of observation. So what is the probability assigned to X under our choice of this Q, right? So we have the choice of the Q, and then we say, oh, this Q is good. Okay, let's see how likely the X was observed under these Z's that are selected by Q minus the KL divergence from Q, so the same Q distribution to the prior distribution. So this is what often referred to as the variational lower bound. And what is really interesting is that So we started from here, right? We started from here. We started from here, and then what was our goal? So our goal of variational inference is to find Q that's going to minimize this KL divergence from Q to P, and then that can be written down as here. And then what you notice first is that this log P of X, this marginal, doesn't depend on Q, because we get the marginal using the prior and conditional only. So this doesn't depend on Q. Now this term does depend on Q. And then this term does depend on Q. So in other words, variational inference is identical to minimizing these first two terms only, because the third term doesn't appear. But then what is this variational lower one? This is the negative of these first two terms. So what that means is that we try to find Q by maximizing this term, this variational lower bound, which indirectly implies that we're trying to so that's what which directly minimize this tail divergence. So we're finding the Q that is really similar to the true posterior distribution. And then the really interesting thing happens is that let's say Q is given, Q is fixed. Somebody gave us amazing Q. Now we can fit the prior as well as the conditional distribution to maximize this lower bound, which is just a negative of the first two terms in the KL divergence. It turned out to be the lower bound to log P of X, the marginal probability. This is a really interesting idea in optimization in general, is that if you have a quantity that you don't know how to compute efficiently, but that you need to maximize, what do? You find a lower bound to the quantity that is more efficient to compute and is extremely tight. So it's a very tight lower bound, and then you try to maximize that proxy instead, so as to rule out all the other bad values of P of X. And then what this actually tells us is that we do both the posterior inference, so find good Q, and estimating the parameters. What are the parameters? Parameters are the ones that are involved in this conditional distribution, right? So in the case of the linear PCA, W and B. Now in the case of nonlinear PCA, that is in fact this F. So we now try to solve two problems simultaneously. Given all the data points that we have, right, X we have, let's try to figure out what is the best Q for each of the X. And simultaneously, we're going to try to figure out, given that Q for each one of them, what is the best F that maps the Z to X. In other words, we solve the problem of, we're doing max over two things. Max over F. And then F is the function that maps the Z to X. And then max over Q1 all the way to Qn. Then this is the sum going from 1 to n. And then instead of maximizing the log probabilities themselves, because we don't know how to compute them, we try to maximize the variational lower bound. Qn log P xn given Z minus KL divergence going from Q n Z P. So far so good, except that there are too many of them. As we've been talking about, we often have the millions, if not billions, nowadays trillions of the data points. And then we can't really have this variational posterior distribution for each and every one of these. We can't really carry them over. It's just too expensive. So then, what can we do? We actually learned what to do last week already. Right? What did we do when the number of the columns grew exponentially with respect to n? When we tried to do the matrix factorization. Sum them, yes, there was a continuous backward representation, but we know that the summation is not that good. So we're going to replace it with a neural network. So what we do is we're going to say that now we're going to max with respect to theta and then max with respect to phi. I'm going to just use this. And then this is a distribution over z given xn is going to be, written as, let's call it g of xn, and then this is going to be parameterized by this phi. And then log p of xn is going to be f of z and theta. Minus KL divergence, the same thing, QZ G xn phi to P of z. So what is this? This capital G corresponds to a neural net that's going to take as input one of the observations, and then it is parameterized using these parameters phi. So it can be any arbitrary neural network that we have learned how to do, right? So if my X was text, I can use transformer to build this G, and then eventually what we can think is that we're going to cut out the one of the final layer, and then make it output two things to define, for instance, a Gaussian distribution. What are those two things for Gaussian distributions? Mean and covariance. So we make just G to output mean and covariance over this Z given Xn. And then what this G becomes a neural net that solves the problem of approximate inference, posterior inference for us. We train a model to do so. Now here F is yet another neural net. Now this time we go the other way around. We're going to go from Z, this vector, and using this complicated neural net, we come down to Xn. Now, interesting thing, if the Xn was text, what did you do? We can make an autoregressive model, again using transformer. And then, but then, just like in machine translation, we have the input. That is Z instead of source n. Then we're going to output one word at a time. And then F can very well be another transform. Right? So what that means is that now this is what often is being called as a variational autoencoder. We build two neural networks. One neural net is the kind of, let's say, approximates the data generating process, right? We build the data generating process. That is that there's some Z. We draw Z from the prior distribution. Given that, we make the observation. Now, the data generating process has many parameters because you have to mapping this Z, the content to the actual thing is not a simple process. So this could be very well a transformer or the recurrent net or whatnot. We have learned a lot of those. And then the second neural net that is G here, which is often called the encoder or the inference network. This one solves the problem of given any observation, so given any new text. Now tell me, what is the Z that would have given a rise to this X via this function F, which is often called the decoder. And that's why it's called autoencoder. In some sense, we start from X, observation. We try to infer Z, and then given the Z, we try to reconstruct X. Because under that infer Z, the X has to be quite likely. Now the last term is one of the two things that were balanced when we tried to look at the posterior distribution earlier. What is this? This says that whatever the Z that is inferred has to be likely under prior, because otherwise we would have never actually sampled the Z in the data generating process. So we tried to balance these two, and trying to learn both of these neural networks. It turned out that we can actually train we can train both networks simultaneously using a gradient descent. And then the choice, as long as we choose this Q distribution to be some distribution that admits the so-called reparameterization, then we can actually backprobe through this entire process of the computing the expectation or approximating the expectation with the Monte Carlo method. Unfortunately, we can't really go into the details for that one. That one is for what Joan and others should teach, and not for me. Now let's just continue on a bit by saying that then what can we use this for in the natural language processing? Let's talk about that quickly. So if you go back to the data generating process, in the data generating process, one way in which we have learned really extensively during this semester in terms of the data generating process for text is the autoregressive model. What was the data generating process we had? Is that there's going to be the first word that's going to be drawn from some prior distribution. So there's a prior distribution on the first word, and then the second word is going to be drawn from the conditional distribution conditional on the first word. The third word is going to be drawn from the conditional distribution conditional on the first two words. Then you see the pattern, right? Fourth one, based conditioned on all three previous words, and then we continue. So this was the data generating process that we have assumed in the case of autoregressive model. And in this case, there's absolutely no hidden vectors or whatnot. And then this was kind of necessary. This is very important to have this kind of data generating process because what is the one thing we know about text is that every word is definitely dependent upon almost every other word. For a fluent text, right? For a very ill-formed text, obviously they can all be like random, independent from each other. But if you want to make a really fluent text, the choice of any word really is dependent upon all the other words. And then this was the one data generating process that has been successful. But another way you can imagine is that there is a number of hidden vectors. And then these actually tell us the content that needs to be written down, right, all together. So jointly, let's say I have T many of them. Let's actually not even do this T. So I'm going to draw, we're going to assume that we're going to draw T prime many vectors that tell us about what should be written down. So that tells us about all the different contents and topics that need to be mentioned in the text. So we draw from these prior distributions, right? We have the prior distribution. And then we have x1, x2, x3, all the way to xt, so that t prime. And what we say is that the drawing, so the generating each of these words is conditioned not on other words. So let's look at x2. So drawing x2 is not based on x1, x3, xt directly, but is conditioned on these hidden vectors, right? The topic vectors. Now, of course, one really important thing is that does that mean that the x2 is independent of x1, x3, and whatnot? That's not true, right? It is independent of x1, x3, and xt given these vectors. But after we marginalize them out and then look at the marginal distribution over x1 all the way to xt together, then they are extremely correlated with each other due to these hidden vectors. So what this tag actually tells us is that whenever you run into a situation where you need to model a highly dependent variables, right? They can be in the output, they can be in the input, whatnot. There are these two approaches tend to be a good alternatives. You can choose either of them. And then in text generation, so far the first one has been a dominant paradigm for the approach, but the second one is definitely an option for you to follow if you wanted to build a text generator. And then interesting thing is, you could very well have just a single vector because the t prime could just very well be just one. And then in that case, it kind of gives you a more interpretable, let's say, approach. That is, you do have a single vector that tells me about the global content of the entire text. And then if I run this inference procedure that we just talked about, in order to infer what the z is, the z vector or the couple of the vectors, those vectors actually tell me what the global content of this input is. On the other hand, if you think about the autoregressive model, we don't really have that. We don't really have that. So we don't really get a nice sufficient statistics of the actual observation. Now let's just look at this part quickly. How would you build such a language model? What do we need? We need the prior. And then as we have learned, prior can be as simple as we want. So we want to say that the single Gaussian is used everywhere. But there's one thing that is missing, right? So the one nice thing about the autoregressive model, we can introduce those special tokens like the end of the sequence, and then make that end of sequence as so-called absorbing state. Once you go in, you never get out. So then that actually gives us a nice way to model the length distribution implicitly. But in the case of this approach, we need to have a way to model the distribution. So we need a separate length distribution. In other words, this T prime as well as T, these two are random variables themselves. So we need then what do we need? We need the prior distribution over the T prime. So how many vectors do we need in order to, how many different topics do we want to write about? So that's going to be T prime. Now the distribution can vary with just exponential distribution or whatnot. And then based on that, you sample from all these Gaussian distributions, standard normal distributions. And then given that, now first, conditioned on T prime, we can now try to estimate T. That can be another one conditional distribution. Given that one and all those Z, we can just use transformer. We can use transformer to go from a sequence of C vectors to the sequence of X1 to Xt. And that's what you've been doing like all along, right? In the lab session, in the lectures, and that's exactly the same thing that you can do. Now, only thing that is a bit tricky is how to do the inference. Now then you want to build the inference network. Again, what would that look like? I want to look at all these xt's, x1 to xt, and then try to infer c1 to ct. Just transformer there again. So it turned out this is a really reasonable alternative to the autoregressive model, and then people often call it a latent variable sequence models. Well, I mean, okay, maybe not people. I just call it latent variable sequence model. If you recall from last week, I'm just making up names as we go forward. And then it turned out for let's say generating a kind of let's say fluent text like in the machine translation, the autoregressive model seems to be much better. But for some other problems like the semantic parsing, there is another type of a problem where you're trying to generate a query language given some kind of let's say query. So you're trying to come up with the machine language that allows you to query a database given the natural language instruction. For that, it turned out that this approach actually works quite well. Not sure why, but and then this second approach turned out to be quite good for let's say protein generation, but that was a bit surprising. Yep. So that actually wraps up today's lecture. And as I said earlier, technical content's all done. You've learned everything that I know myself, and I've been doing okay professionally. So you all can do well from here on. So the next week, a bit more on the kind of let's say side effects or the kind of let's say inherent limitations of natural language processing. See you next week then.